Thanks for your invitation. And in this section, we will talk about the renewable energy at the resilient city. So everyone knows, so photovoltaic has been widely used in many places in China and all around the world, especially for the weather, for the energy power supply for the future city. So at here, PV not only can be used in the wild places like a rural area in China, but also has been widely used in the city. So PV has been integrated with buildings, let's say BIPV, and to power supply for the electric energy consumption for buildings, and also some sub-city areas. The PV also have been popularized on the roofs to generate more electricity, especially for factories. A lot of factories, they have larger area of roofs. Okay, it is very convenient for the factory owners to install larger PV that can minimize their energy consumption from the power grid. However, okay, there are a lot of risks has been occurred in the city application, like fires, like non-uniform agent, because in the city the pollution in the cities, okay, the rain is not a pure water that integrates in some chemical elements that can speed up the aging of the PV modules, and also bird drops like shadows and dusters. All those things has been influence the efficiency, reliability of the PV modules. In this slide, we will just give you some information on progress we have done in the research area, like for diagnosis, safety operation, high efficiency operation at 40 condition, engine management for larger scale PV array, and soil management and non-uniform agent array PV efficiency improvement. All those 6 areas we have been doing in this area for more than 15 years. So I just share you some information about it. For example, how can we do for diagnosis for larger scale PV array? So we have posed a theory, how can we find 40 modules in a PV stream? So we just compare the voltage of each modules, and we also can find the 40 PV modules in a larger PV array. That means we just the first step is find the 40 stream, and then use the voltage comparing method to locate which module is broken. So by this method means we need a huge number of sensors, like current sensor and voltage sensors. So how can we decrease the sensor numbers? So we proposed minimized sensor location method. So like this way, we just by sensor placement cover all node points. So by our method, we also can use our algorithm to remove the current sensor for each stream. That can further decrease the cost of sensors. So that method only works for a small scale sensor, but for small scale of PV array, for larger PV array, so thermal camera will be a most convenient method, or with a mainstream method. And here, so we find the structure of a PV module that composed of like PV cell, junction box. So we can categorize the PV module fault into 3 kinds of fault. We say, heavy fault. That means the schedule or broken PV cells that block the current goes through the cells. Okay, the current only goes through the bypass diode. And then we also have some, minor fault. The minor fault means the current can still go through the other parts of the PV cells. Okay, in these scenarios, the faulty area will become resistant, and that area so it can be heated by the electricity power. So that is the reason we can find the phenomena of hot spot. And another, air fault is the middle one. So we can see the example of the heavy fault. So we mimic the heavy fault, use wood on the surface of a solar panel. So we can see in this string or in this cell unit, there's no power go through it. So that is zero electricity output. So the electricity only goes through the diode. So we can see the surface temperature is different with this healthy one and unhealthy one. So we can go through, find another one. We can see the mismatch fault. So we just use a paper cover on a surface of a PV module. We also can see the thermal image difference. One difference is temperature. The other difference is the faulty area. So we can go through another scenarios. The open circuit fault and the short circuit fault. We can see the thermal image temperature difference is totally different in electrical thinking. So all those faulty conditions are has very similar terminal electrical output characters, but for the thermal image they are totally different. So we did some experiment to compare the temperature distribution under a faulty condition with two different working points. So we can see at the point A, so the temperature for healthy stream is higher than unhealthy stream. For point B, we find that the unhealthy stream has higher temperature than healthy stream. So that means just only compare temperature difference, we cannot locate which stream is in healthy or unhealthy. So that means purely while thermal image, we cannot find the right conclusion for a health condition for a larger scale PV array. So and here we also propose the bridge gap of the fault diagnosis and the real-time operation with a maximum power point in real time. So and here we propose an algorithm to use the thermal image information and then by wire that information to find maximum power point tracking for the larger scale PV array. So this is, we also developed the algorithm for the non-uniform aging PV array to improve its efficiency. We can see for a larger scale PV array, there is a clear bucket effect of the non-uniform aging PV cells. So this we propose a method to detect the PV aging map. So we can have the thermal cameras, we can use TDR radars. So, and when we get the PV non-uniform aging map like this one, so we can propose the online or offline reconfiguration method to make the PV array improve efficiency without replace a new PV modules. And then this is for the case study of larger PV. It's about it's 20 PV array. It's about 400 kilowatt larger scale PV array. By our algorithm, we can improve the efficiency by 10% without change, without replace any new PV modules. So we do some experiment to verify our algorithm. Yeah. So by this is 2 times 4 PV array. So we just swap some places of PV module. We can improve about over 10%, about 20% energy output enhancement. And my student also did some calculation, consider about labor cost and the electricity fee, benefit for PV modules, PV arrays in different countries. So we did some calculation compare Saudi, Pakistan, India, France, United Kingdom, Germany, and China, and the United States for the same case with different country, because different country has different electricity fee, different labor cost. Our method works very well in some specific country. For example, so it works very well. It works in like in Saudi and the United States, and the United Kingdom also works very well. So this is a comparison, for the our proposed method is that works for different countries. Yeah. So I will skip this one. And then finally, we discuss about how can we sort out the soiling problem of the PV modules in the cities. In the cities, the dust is a long-lasting problem that can decrease the PV module efficiency and also can result in some disaster like a fire. So we analyze the dust distribution on the PV modules with different wind and some different environmental conditions. So we did the simulation, and we can predict which is the best timing for the PV owners to clean it. Yeah, so we did some simulation and for it. And last but not least, so we also did some analysis for fire risk analysis for the city, because the city fire is the biggest disaster. So here, example of the burning area of PV roofs in London. So we analyze the fire, and we also propose our solution to mitigate the fire risk for the PV roofs. So we just escape for it. So we just go to summary. So what we have done, we did 6 experts on PV array management, like PV for diagnosis and fault tolerance operation, soil management, safety operation, agent estimation, and efficiency improvement. So I hope those 6 steps could improve PV application in city to improve reliability and its efficiency. So that is all my slides. Okay, thank you.